Hello students, welcome to EPG Pathshala. I am Dr. Maimuna Akhtar from School of Pharmaceutical Education and Research, Jamia Hamdard. Here we are going to discuss about the module Instrumentation used in Atomic Absorption Spectroscopy from paper Atomic Spectroscopy. After completing this module, you shall be able to understand the basic principle of atomic absorption, the operation of the instrument, various parts of the instrument used for measurement, importance of burner, nebulizer and sample atomizer used in the instrument, how to select a particular wavelength and its impact. We already know that atomic absorption spectroscopy is based on absorption by atoms or elementary ions. The components of a sample are converted into gaseous state or elementary ions by suitable heat treatment in atomic absorption spectroscopy. These atoms then get excited and the absorption is measured at a selected wavelength, which is characteristic to each individual element. The absorbance of the gaseous mixture serves for qualitative and quantitative determination of one or more of the elements present. Qualitative means you can distinguish each and every element, and quantitative means you can determine the quantity of the particular element. The potential of atomic absorption is such that it can be used to analyze at least 62 elements. The process of converting sample into vapor is called atomization, and the precision and accuracy of this procedure in atomic absorption spectroscopy are critically governed by this step. The components of atomic absorption spectrometer. The basic components of any type of atomic absorption spectrometer includes light source, burner or nebulizer, sample atomizer, wavelength selector, a detector, and readout device. This figure shows you a schematic flow chart of atomic absorption spectrometer. A light source, which can be any kind of lamp, mercury arc lamp, incandescent lamps, followed by a flame which is produced by different fuels, mixture of fuels. A nebulizer pumps the sample in a certain type of mist spray, sample container, then monochromator, which are used to select a particular wavelength, a wavelength of interest, the detector, and then data processor and recorder. Coming to light source, commonly two types of light source are used. One is hollow cathode lamp and electrode discharge lamps. The hollow cathode lamps consists of the common source of light in atomic absorption spectroscopy. It consists of a cathode which is hollowed out cylinder made of the element to be determined and a tungsten anode. Hollow cathode lamps are of two types. One is single element lamp and another is multi-element lamp. The single element lamp are generally made from very pure metal, whereas multiple element hollow cathode lamps are constructed from a mixture or alloy of several methods. The figure is an expression of any hollow cathode lamp. Electrode-less discharge lamps. Electrode lamp discharge lamps have been taken as better alternative for more volatile elements where low intensity and short lamp life are limitations. Electrode-less discharge lamp is constructed of a quartz bulb filled with an inert gas containing the element or a salt of the element for which the lamp is to be used. A typical electrode-less discharge lamp is shown in figure. So coming to next part of the instrument, that is a nebulizer. Nebulizer refers to an apparatus that converts liquid into a fine mist. Nebulization is process in which the sample is converted into fine mist of finely divided droplets. There are two types of nebulizers used in atomic absorption spectrometers. The pneumatic nebulizer and ultrasonic nebulizer, that depends upon the requirement. Pneumatic nebulizers are most common type of nebulizers used, and there are three types of pneumatic nebulizers which are very common. and they are called concentric tube, cross flow, fritted disc. And the figure in the next slide shows you various types of pneumatic nebulizers. Different types of pneumatic nebulizers. A is concentric type of nebulizer, wherein the sample and argon are mixed at a T-point. In figure part B, a cross-flow pneumatic nebulizer is shown, where the sample and the argon gas encounters at 90 degrees to each other. C is a Babington nebulizer. D is single bore high pressure pneumatic nebulizer, and E is microwave thermal. Ultrasonic nebulizer. In ultrasonic nebulizer, the sample is fed to the surface of a vibrating piezoelectric transducer operated at a frequency of between 0 to 10 MHz. The mist obtained is most homogeneous and denser than pneumatic nebulizers. Sample atomizers. Sample atomizer is that part of atomic absorption spectrometer which converts the analyte into gaseous atom, and it is known as the lifeline of the instrument. Main two types of atomizers include discrete atomizer and continuous atomizer. The discrete atomizers include electrothermal atomizer. It's a device which is heated to the temperature required to analyte atomization by the passage of electric current through its body. Whereas in case of continuous atomizers, flame is used to atomize the sample. Flame atomizer is oldest and most commonly used atomizer in the atomic absorption spectroscopy. After the sample is nebulized, it is carried into a flame where the process of atomization takes place. Once the sample reaches flame, 3 steps takes place. First is dissolution, second is volatilization, third is dissociation. In step 1, that is dissolution, the solvent is evaporated to produce molecular aerosol, which is followed by conversion of the sample to gaseous form and to form the aerosol. And the last step, that is dissociation. In this step, the atomic gas formed by the dissociation of molecules is produced. In this process of ionization of atomic gases, some cations and electrons are also formed. This slide shows you the mixture of fuels and oxidant that are commonly used in flame atomizers. Left extreme corner column shows you oxidants, the second is fuel, third is the temperature they produce, and the last column is the maximum burning velocity. For example, by mixing oxygen and natural gas, a temperature of 2700 to 2800 degrees centigrade can be obtained with a burning velocity of 370 to 390 centimeter per second. The highest temperature is obtained with oxygen and acetylene, that is 3050 to 3150, with a burning velocity of 1100 to 2480 centimeter per second. Air acetylene also produces high temperature, that is 2100 to 2400, with a burning velocity of 158 to 266 centimeters per second. Nitrous oxide and acetylene produces 2600 to 2800 degree centigrade temperature with a burning velocity of 285 centimeters per second. Now it is very important to select a wavelength. Why? We know that the difference between the two energy levels is very definite. So therefore a wavelength which has specific energy related to it should be supplied so that molecules absorb that amount of radiation and no noise is produced. So wavelength selectors limit the radiation absorbed by a sample to a certain wavelength. A radiation of narrow, limited, continuous group of wavelength is very desirous for any spectroscopic analysis, because it enhances the sensitivity of the absorbed, it enhances the sensitivity of the absorbance measured. It also helps in obtaining linear relationship between the optical signal, that is absorption or emission, and concentration of the analyte. Ideally, a wavelength selector should be able to produce radiations of single wavelength or frequency. But that is not the reality. Types of wavelength selectors. There are various types of wavelength selectors, and most commonly known are filters and monochromators. The two types of filters are mainly employed for wavelength selection. One is called interference filter and another is called absorption filter. Absorption filters are restricted to the visible region of the spectrum, whereas interference filters are used for the ultraviolet, visible as well as into the infrared region. The first kind of filters among the filters used for selection of wavelength is interference filters. They work on the concept of interference, as the name suggests. By optical interference, they provide a narrow band of radiations. It consists of a transparent dielectric material, for example, calcium fluoride or magnesium fluoride, that occupies the space between two semi-transparent metallic films. This area is sandwiched between two plates of glasses or other transparent material. The dielectric layer thickness is controlled carefully as it determines the wavelength of the transmitted radiation. When a perpendicular beam of collimated radiation strikes this array, a fraction passes through the first metallic layer while the remainder is reflected. The portion that is passed undergoes a similar partition when it strikes the second metallic film. If this reflected portion from this second interaction is of proper wavelength, it is particularly reflected from the inner side of the first layer in phase with incoming light of the same wavelength. The result is that this particular wavelength is reinforced, while most other wavelengths being out of phase suffer destructive interference. The interference filters are available with transmitter peaks throughout the ultraviolet and visible region and up to about 14 micrometer in the infrared. Interference wedges have also been used as wavelength selectors. An interference wedge consists of a pair of mirrored, partially transparent plates separated by a wedge-shaped layer of dielectric material. The length of the plates range from about 50 to 200 millimeter. The radiations transmitted varies continuously in wavelength from one end to the other as the thickness of the wedge varies. By choosing the proper linear position along the wedge, a band width of about 20 nanometers can be isolated. Interference wedges are available from the visible range 400 to 700 nanometers, the near infrared region that is 1000 to 2000 nanometers, and for several parts of the infrared region 2.5 to 14.5 mu micron. They can serve in place of prisms or gratings in monochromators. Absorption filters. Absorption filters have been widely used for band selection in the visible region as they are less expensive than interference filters, but the performance is inferior to those of interference type of filters. These function as absorbing certain portion of the spectrum. The most common type of absorption filters consist of colored glass or of a dye suspended in gelatin and sandwiched between glass plates. The colored glasses have advantage of great thermal stability. Absorption filters have effective band width that ranges from 30 to 250 nanometers. Filters that provide the narrowest band width also absorb a significant fraction of the desired radiation and may have a transmittance of 10% or less at their band peaks. Glass filters with transmission maxima throughout the entire visible range are also available commercially. The cutoff filters have transmittance of nearly 100% over a portion of the visible spectrum, but then rapidly decreases to zero transmission over the remainder. A narrow spectral band can be isolated by coupling a cutoff filter with a second filter. So when filters do not serve the purpose, monochromators are the best choice. So in addition to filters, they are suited for wavelength selection. The name monochromator is derived from the Greek root mono, means single, and chroma means color, and the Latin suffix ater denotes an agent. A monochromator is an optical device used to transmit a selectable narrow band of wavelengths of light or other radiations chosen from a broad range of wavelength at input or output level. A monochromator either uses the phenomena of optical dispersion in a prism or diffraction from diffraction gratings to specially separate different wavelengths. Components of a monochromator. A monochromator consists of an entrance slit that provides a rectangular optical image, a collimating lens or mirror that produces a parallel beam of radiation, a prism or a grating that disperses radiation into its component wavelengths, a focusing element that reforms the image of the entrance slit and focuses it on planar surface called a focal plane, and the last part is an exit slit in the focal plane that isolates the desired spectral band. In addition, most monochromators have entrance and exit window, which are designed to protect the components from dust and corrosive laboratory fumes. There are two basic types of monochromators that are used. One is grating monochromator and another is prism monochromator. Grating monochromators are based on diffraction and interference. There are two types of gratings. One is transmission grating and another is reflection grating. And they consist of a series of grooves in a glass or quartz or even a mirror. A grating is a simple plate wherein you can create grooves in any plate. That can be thousands of grooves in 1 centimeter. So the grooves are so close to each other. Gratings. A transmission grating consists of lines that are ruled on glass and the unruled portion acts as the slit. Reflection gratings. The lines are ruled on a polished metal surface and the incident light is reflected from the unruled area, producing by reflection the same result as that by transmission through the transmission grating. Depending upon the shape of the ruled surface, one can also distinguish between plane and curved grating. Curved reflection grating have focusing capability depending on the radius of the curvature of the surface, which will be superimposed on the diffraction effect of the grating itself. Types of grating monochromators. Two types of gratings have been used in monochromators. One is Eschel grating and another is Escheled grating. In first case, short face of the groove is used for dispersion of the radiation. You can see from the figure on right hand side. In Escheled grating, long face of the groove are used for the linear dispersion of the radiation. There are also concave gratings available. These gratings can be formed on a concave surface in the same way as on a plane surface. A concave grating permits the design of a monochromator without auxiliary collimating and focusing mirrors or lenses because the concave surface both disperses the radiation and focuses it on the exit slit. Such an arrangement is advantageous in terms of cost. It also reduces the number of optical surfaces, increases the energy throughput of the monochromator. Prism monochromators. Prisms have also been used as a monochromator. They are used to disperse ultraviolet, visible, and infrared radiation. The material used for their construction differs, however, depending upon the wavelength region that is in work. It creates angular dispersion by refracting the light at the surface of two interfaces. The parts of the prism monochromator is shown here. It consists of an entrance slit, a collimating lens, a prism, a focusing lens, and an exit slit. So after selecting the particular wavelength, it is important to detect it properly. The detectors used should have certain important characteristics. That includes, it should have good response to the wavelength of selection. It should have good quantum response. That means it should be able to detect light. It should have a good sensitivity. The frequency of response, that means it should be very fast. The response should be speedy. Also, the stability is important factor. Then one of the most important factors is cost and convenience. Various types of detectors are available, ranging from photodiode to photomultiplier tube. Photodiode is a kind of light detector that converts light into voltage or current, which is generated from the absorption of photons. A PN junction or photovoltaic detector. This is made of two types of semiconductor materials. One is called P-type and another N-type. P-type material are acceptors like aluminum, boron, lanthanum, and gallium. Whereas N-type of material is donor, that is arsenic, tin, or lead, or phosphorus. Both types contain silicon crystals, which is commonly used in semiconductors. Another type of detector is photodiode array. It consists of individual photosensitive elements called photodiodes. It has a linear array of discrete photodiodes placed on a large integrated circuit of a silicon chip than a single photodiode. Photodiode array works on the same principle as simple photovoltaic detector. And last but not least is the photomultiplier tube. Photomultiplier tube is a versatile device. It has extremely high sensitivity and is used for measurement of low radiant power. It converts photon to electric signal, in contrast to photodiode. Photomultiplier tube. The figure shown here is a high sensitivity photomultiplier tube used in luminometry. In photomultiplier tube, all the electrons released from photocathode practically hits the first diode, where a number of secondary electrons are generated, roughly between 4 to 6 electrons for each hit. These are then accelerated to the next diode, so on and so forth. After hitting each diode, the signal grows exponentially until an avalanche of electrons is formed, which finally hits the anode. From anode, the charge are picked up by the electronic process with a typical electron multiplication factor of 10 to the power 6. Then when you have done all, you have recorded, but you need a readout device then. Several types of readout devices are used in modern instruments. These devices include digital meters, recorders, cathode ray tubes, LCD panels, and computer display, etc. So students, let's summarize what we have learned in this module. We have brushed up the basics of atomic absorption spectroscopy. We have discussed the various parts of instrument used for measurement of the light generated in atomic absorption spectroscopy, various types of nebulizers and atomizers used to create the mist, importance of burner and nebulizer along with the sample atomizer, the various types of monochromators used, the gratings and prism monochromators, their advantage. Thank you.